The subject of my talk is unified approach to accurate and efficient modeling of composite beams, plates, and shells. I am delighted to be able to give this presentation, even though I am sorry that I am not there with you. Beam-like structures are ubiquitous in the field of engineering. We have rotor blades for helicopters. We have high aspect ratio winged aircraft. We have beam-like structures in highways and bridges and buildings, wind turbine blades and towers. And what do these all have in common? Their theories are asymptotic approximations of 3D elasticity in terms of small parameters. One dimension, for example, of a beam is much larger than the other two. One dimension of a plate or shell is much smaller than the other two. So what does it matter? Well, models based upon these theories they have significant advantages over 3D finite elements and 3D elasticity in the areas of efficiency, ease of interpretation of results, and ubiquity of analysis tools in industry that rely on the simpler analyses. These models are frequently appropriate for lifting surfaces, as we will see. The methodology that I'm going to make use of is something called the variational asymptotic method. It's a systematic mathematical method. It reduces 3D elasticity to beam, plate, or shell theories by the exploitation of small parameters. It was proposed over 40 years ago by Professor Victor Berdichevsky, who is presently at Wayne State University, but was previously at Moscow State University. This method asymptotically expands energy functionals or variational principles in terms of small parameters. It converges asymptotically to 3D elasticity solutions and leads to engineering models for multiphysics built-up smart structures made of inhomogeneous composite materials regardless of internal complexity. It combines the merits of variational and asymptotic methods. Here's an illustration showing 3D elasticity on the far left of the screen, and either splitting the problem by small parameters into a beam or a plate and shell, we come up with reduced order models, beams being one-dimensional analyses with a two-dimensional cross-sectional analysis, or plates and shells being a one-dimensional through thickness analysis with a 2D analysis for the plate or shell surface, and then recovery relations that allow you to recover 3D stress, strain, displacement, etc. This is what real helicopter blades may look like. They're very internally complex, and without some kind of way of representing this complexity, there is no hope of accurately modeling such a structure. But with this methodology that I'm talking about, we certainly can do all that we need to do to create a cross-sectional analysis and a one-dimensional analysis, for example, for the rotor blade. And we use a small strain assumption, which is necessary for nonlinear analysis. And the structure is very slender, which provides the motivation for using beam models. Beam theories that are not asymptotically exact make use of assumptions which not only may introduce approximations, but may fail to capture the correct behavior. So VABS is our beam cross-sectional analysis tool, and it is here being used to model the cross-section of a rotor blade. Makes a finite element discretization of the sectional geometry, can be used independently for structural design, and it rigorously models composite sections with negligible additional cost to the rotor blade analysis. And it enables designers to abandon the black aluminum approach and actually take advantage of the 3D properties of the composite. Here is a composite strip. It's a simple structure. And we take the 3D material properties, which are on the far left of your screen, and we use VABs to get on the lower right a set of stiffness constants for this beam. We also get inertia properties, as in the lower left part of your screen, and we can calculate natural frequencies and mode shapes. Here, the natural frequencies are tabulated along with the natural frequencies obtained from 3D finite elements. You can see there's very little difference in the two. And the mode shapes, aside from the fact that these are slightly different views, the mode shapes are essentially identical. What's not identical is the efficiency. The 3D finite element program required 92 seconds to run, and it needed 30,000 degrees of freedom. Our reduced order approach took 1,000 degrees of freedom for VABs, gave us a 1D solution in 1 second and VAB solution in 0.2 seconds, and we get essentially the same answers. Now, beam models may falter near the end of a beam or near a discontinuity. We understand. Here is a thick composite, something you would probably never build, but this puts the methodology to the test. We take a beam with a cross section like this and we apply a shear force at the tip with cantilevered conditions, and we get, if we run a 3D finite element, we have about 1 hour on a PC, whereas with VABs we take less than a half second, and the 1D solution can be obtained by inspection. We can recover the transverse shear stress such that there's no discernible difference between the results from VABs and from our 3D analysis that was done with ANSYS. Here is another transverse shear recovered in the other direction, and again you can see the details with which it is possible to recover 3D stress. We can look at initially curved and twisted composite beams. Here is a situation where the beam has a strip-like geometry, and it has either a twist per unit length, which we call little k1, varying from 0 to 0.05 radians per inch, or k2, a curvature, which has the same variation, and the material in both cases is a graphite epoxy with the layup specified here. Now we get natural frequencies here that are essentially the same through the first eight or nine modes. You can start to see a little bit of a discrepancy up in the highest mode that is displayed here. This with the curved anisotropic beam, similar but maybe even better results are obtained. We also can get results for a helical spring, which we could model it as an initially curved and twisted beam. And when we put it together with a 1D code, we have a code in-house we call Natasha. Natasha takes a total of 13 seconds, and the frequencies are within 1% of those obtained from the 3D analysis, which takes 11,000 degrees of freedom and 3 full minutes of runtime. And the results are essentially the same for these first 9 or 10 frequencies. This is an example of stress recovery for an actual helicopter rotor blade section, courtesy of Bell Helicopter. This is a wind turbine blade, and you can see that the mesh is very, very fine as we have blown up the indicated region near the trailing edge to zoom in at the bottom of the screen there. And then we've changed the temperature, the ambient temperature, and looked at the stresses induced, and it is almost impossible to tell the difference between results obtained from VABs and results obtained from a 3D analysis. And here are some stresses displayed through the thickness. We can do the same thing with composite laminates. Plates and shells are very common in engineering analysis, for example. Most popular engineering plate and shell theories are based on either classical laminate theory, which is a Kirchhoff-Love model, or a generalized Reisner-Mendlin model, which some people call first-order shear deformation. But we don't make those assumptions. We use a tool that's very similar to VABS called VAPAS, which calculates the elastic constants for a plate or shell, and we have run it here on a 20-layer plate under a sinusoidal mechanical surface pressure. And you can see that VAPAS gives results that are right on top of 3D elasticity, whereas first order shear deformation gives results that are essentially worthless. Here is a composite laminate that's loaded on the top with a sinusoidal load in both X and Y directions. And we have now captured using a bunch of different plate theories, which include plate theories that are zigzag models, that are higher order models, that, you can see here that these higher order models, all of them have different numbers of degrees of freedom. Some of them that give the best results, for example, here's one that's 39 degrees of freedom per node, and it gives results that are right on top of 3D. But here's VAPAS with 5 degrees of freedom and gives the same answer. And this is for recovery of displacements. If we want to recover stresses, same kind of thing. Even the best zigzag theory is not as good as VAPAS, and the best zigzag theory has twice the degrees of freedom. And these are highlighted here for your convenience so that you can see that the results here are truly excellent. Here is another way of displaying the results, and you can see that the closest results to the full 3D elasticity results are those from VAPAS, and they're better than any of the other approaches that are displayed here. Same thing with multi-physics plates. 3-layer piezoelectric plate with the properties given here. And again, you can hardly distinguish the results between VAPAS and the 3D approach. There is now a new development that has come out of Purdue University from Professor Wenman Yu, who has developed something that he has dubbed the mechanics of structure genome approach. It is another way of applying the variational asymptotic method, which gives results similar to VABS for beams and VAPAS for plates and shells, but it also allows you to dimensionally reduce a wide variety of structures, and it is truly an amazing approach. Here are some examples of that type of analysis where VAPAS, or rather VAPAS, could have been used on this model that's to the left of your screen, but now the mechanics of structure genome gives you results for these much more complicated structures in the middle and on the right. And so the company that they have formed markets this code under the name SwiftComp. There are many examples I could have given, but you can see the complexity of this kind of structure. This, for example, is a 3D orthogonal interlocked composite, and the results are essentially identical with what you get with 3D. In looking at displaying results through transverse compression loading of a laminate, you can see here that there is some very, very complicated behavior, especially toward the bottom of your screen, that the mechanics of structure genome is able to recover that are essentially identical to those of 3D elasticity. Same thing with biaxial extension, a very complicated structure and amazingly accurate result. Now, some of our most recent work is looking at the question associated with drilling stresses and stiffnesses of plates made of foam. We have looked at the Kosarat elasticity model as a starting place, and my recent student, Ravi Kovali, developed, using the variational asymptotic method, a structural model for the Kosarat plate. And this is one way, and in fact, it's the only way that I know of to get the drilling stiffness constant for a plate, because it has degrees of freedom that are not present in a full-blown 3D classical elasticity approach. So we were able to get closed form expressions for plate elastic constants, including the so-called drilling stiffness. And here, for two materials, are the stiffnesses as displayed as a function of the length parameter that is associated with Kosarat elasticity. Now, people have said, well, computers are just getting faster all the time. Who needs these reduced order models? We can just run 3D elasticity models and be done with it. Well, we've already seen how computationally expensive that can be. But it's not time to abandon beam-based modeling of things like rotor blades yet. Industry tools based on beam theory are ubiquitous. Much more can be done and should be done to improve them. The hybrid 3D and beam models can take advantage of the fact that for almost all of a rotor blade, a beam model is just fine. And then you can use 3D tools for the parts of the beam that cannot make use of a beam model. And here is an example of two uniform beams. At the root here, which is on the left part of your screen, we see that there is a cluster of 3D elements, and those are put there to pick up the behavior of the beam near its root end, which is something that ordinary beam theory doesn't capture well. And also at the point where the properties change there in the middle, we see that there's a cluster of 3D elements there. But when we run both our code and the 3D code for this particular case, we see that there's hardly any difference in the first 14 natural frequencies here. They are essentially the same. So in conclusion, I have presented a systematic approach for modeling composite lifting surfaces and in two sets of equations that come from the common framework of 3D for beams and as well as for plates. For beams, we have a degree of rigor and power that would be impossible with the older paradigms that I faced when I was right out of graduate school nearly 50 years ago. There's no restrictions on the cross-sectional geometry or the materials. This is a We can also create a sort of hybrid analysis based on joining together 3D with beam models if we need the extra accuracy in certain places. And we get the geometrically exact 1D equations. I said very little about that, but it is a very important thing to have geometrically exact equations. That way you don't have to worry about keeping track of the orders of magnitude of all the terms like we did in the old days with so-called ordering schemes. Now for plates and shells, we can similarly reduce those, and I spent some time showing results for our code VIPAS, but also for the mechanics of structure genome methodology. I'd like to acknowledge the sponsors of this work. Over the last 3 decades, the work was supported by the U.S. Army primarily, but there are many other sponsors that are listed here too, without whose help we couldn't have brought this to pass. I also had an amazing amount of really excellent graduate students and time together with them, extraordinarily talented people. And you can see the names of many of these that you would recognize, I'm sure, as being people who have themselves made excellent contributions in this field. Thank you very much.